Okay, so we've looked at the arithmetic series in the previous video. We're now going to look at the geometric series. So a geometric series, a simple definition is when a sequence increases or decreases by a common ratio. So an example of a geometric series would be, for example, 2, 4, 8, 16, 32. Because we are increasing by 2, a ratio of 2 every single time. Another example might be 10,000, 1,000, 100, 10, 1, 1 over 10, 1 over 100, because we are decreasing by 10 every time, so I can rewrite it as multiplying by 1 over 10 every single time. So these are two examples of a geometric series. And from here, we can work out, or we need to know the end term equation. So we have un is equal to a times r to the power of n minus 1. Once again, like the arithmetic series, a represents the first term, and r represents the common ratio. And obviously, n is just the end term. And so therefore, for this example here, example number 1, our a will be 2, our r will be 2 as well. So the end term for this first sequence would be 2 times 2 to the power of n minus 1. For the second one here, our a, the first value is 10,000. Our r is 1 over 10, so the end term un is equal to 10,000 times 1 over 10 to the power of n minus 1, like this. So that's how we find the end term equation. Along with this, we also need to know the sum equation. So Sn is equal to a times 1 minus r to the n over 1 minus r. Or you might see it the other way around, so a times r to the n minus 1 over r minus 1. So they're both the same equation. You can use either one, whichever one you are more comfortable with. As we said in the curriculum, we need to know how to prove these equations as well. So let's go about proving the sum equations. So I'm going to rewrite the sum as just each individual terms added together. So the first term will be a, second term will be ar, third term will be ar squared, ar to the power 3, and so on. The second to last one will be ar n minus 2, and the last term will be ar n minus 1. Now, for the arithmetic one, we just rewrote it back to the front, right? But for this one, what I'm going to do is now times each term by r, okay? So a times r would be equal to ar, which I'm going to write here. Ar times r will be ar squared, so I'm going to write that underneath here as well. And so on, like this. And finally, if I was to times the last term by r, I'll be left with ar to the power of n. What we can do now is actually subtract each term from another. So on the left-hand side, I'll get Sn minus r to the power of Sn. And on the right-hand side, what you'll notice now is if we subtract it, then these ones, these pairs will all cancel each other out. And what we're left with is actually this term here, a, and because we're subtracting it minus this last term here, a to the power of ar to the power of n, which I can now factorize. So on the left-hand side, Sn, 1 minus r, a 1 minus r to the n, and dividing it will leave us with the sum equation. Like so. So make sure that you're very familiar with this proof, because once again, you do need to know how to do it. So maybe try it yourself and come back and check your answers with this here. And finally, from here, we can actually work out one more equation for geometric. There's something called a sum to infinity equation. And that is s to the infinity is a over 1 minus r. Now, this is used to work out what's the sum from the first term to the infinitive term, okay? And so you can use this equation here. And it's derived from the sum equation, but it only works for a certain value of r, and that r, or the magnitude of r, has to be less than 1. Now, this is important because if I go back to the sequence 2, 4, 8, 16, 32, as you can see, we're increasing by 2 every single step, right? So when it gets bigger and bigger, the values themselves are going to get bigger. So if I wanted to sum them all up, it would be impossible because at the very large values, they just keep increasing, so it won't pinpoint to a certain position. This sequence here is known as a diverging series. So for a diverging series, this occurs when the magnitude of r is bigger than 1, we cannot work out the sum to infinity. This is impossible. For a convergent one, for example, if I say 32, so I go the other way around, you can see now that the terms are getting smaller. And so by the infinitive term, it would be like a point or very close to zero, right? But in this case, we can actually work out a equation or an answer, as this is known as a converging series. And that occurs when the magnitude of R is less than 1. So for a converging series, we can use this equation here to work out the sum to infinity. For a diverging one, we cannot do it. We cannot actually work out the sum to infinity. So that's all the theory you actually need to know for the geometric sequence. It's just a matter of now applying this to exam questions. Okay, so let's take a look at this question here. So we're told that a geometric series has the first term 1200 and the sum to infinity is 960. And so we can say, using the sum to infinity equation, it's a over 1 minus r. We can say that 960 is equal to 1200 divided by 1 minus r. 1 minus r is 1200 over 960, which is 5 over 4. So r, we get negative 1 over 4, and that's what they asked us to find in part A. In part B, it says find to 3 decimal places the difference between the 9th term and the 10th term. So now, rather than the sum equation, we're looking at the nth term equation here, right? So just to write out the general nth term equation, our A is still 1200. Our R is negative 1 over 4, so I'm going to write that as a bracket to the power of n minus 1. And so they want us to find the difference between the 9th and the 10th term. The 10th term would be 1200 times minus 1 over 4 to the power of 10 minus 1 is 9. The 9th term would be 1200 times minus 1 over 4. 9 minus 1 is 8. And if I find a difference, I'll get negative 0.229. It's just a matter of using or finding the general nth term equation and then finding a difference between the two terms. Right. Write down an expression for the sum of the first n terms of the series. So they're asking us now for the sum equation. So Sn is equal to a times 1 minus r to n over 1 minus r. A is 1200. We have 1 minus a quarter to the power of n over 1 minus a quarter. And obviously you can simplify this a bit. So I'm going to get 1 to 100, 1 minus 1 over 4 to n over 5 over 4. And this will give me 960 times 1 minus a quarter to the power of n. This is a sum equation for this particular geometric equation. And finally, prove that the sum of the first n terms is this here. And it says given that n is odd. So this is important, or the way we work this out is, if we look at this here, the r value is negative a quarter, right? So if we, for every time we change it, it'll be odd, even, odd, even, odd, even, right? So the minus side will change from minus, plus, minus, plus, minus, plus. So what I can do instead now is say 960 times 1 minus, and I can split it up saying it's minus 1 to the power of n times a quarter to the power of n. As this is the same thing as the original minus 1 over 4 to the power of n. And so for n is odd, minus 1 to the power of n becomes minus 1. And if we have minus 1, then it becomes plus 1, right? So we're going to have Sn is equal to 960, 1 plus a quarter to the power of n. And this is only for odd values of n. So as you can see, the equations themselves aren't too difficult as long as you pinpoint or you understand what equation to use and what your A and the common ratio values are. Let's just try one more question. So we say have an adult population of the town is 2,500 at the end of year 1. A model predicts that the adult population will increase by 3%, forming a geometric sequence. Calculated predicted adult population of year 2 is 25,750. So they've told us that A, so initially, is 25,000 people, and R, they say, is increasing by 3%. So we have to say it's increasing by 3%, meaning it's going to be 1.03. That's how much it's going to increase by. So now we can just say, find the nth term equation. So we can have 25,000 times 1.03 to the power of n minus 1. And so at the end of year 2, so n is 2, just plugging in n is 2, we'll actually be able to show that it's equal to 25,750. B is asking us to write the common ratio. Well, we worked out already, right? So it's 1.03, so that's quite simple. C, the model predicts that year N will be the first year in which the adult population will exceed 40,000. Show this. So we're looking at the N term equation, and they're saying at a certain value of N is going to exceed 40,000. So we can create an inequality like this. And so we can now rearrange this. So I can say that 1.03 N minus 1 is equal to or greater than 40,000 over 25,000. If you simplify that, that becomes greater than 1.6. And now we want to bring the n, which is in the power, down, right? And what we can do is apply logs. So we have n minus 1 log 1.03 is bigger than log 1.6. And that is what they want us to find or show in part C. And indeed, it says find the value of n. So it just means we have to use this equation we found in part C to find what n is going to be. So it's just a matter of just simple log manipulation. So we'll just divide by log 1.03. So we get log 1.6 over 1.03. N minus 1 is bigger than log 1.6 over 1.03 plus 1, which will give me n being bigger than 16.9. And once again, because n has to be a full integer, or just integer numbers, n has to be equal to 17, like this. All right, so that's the end of the geometric videos. As long as you don't get confused between the arithmetic and the geometric series equations and letters, then you could probably be able to answer most exam questions. Just remember to clearly state what A and R are, and then understand which question or which equation they are asking you to use. If you have any questions, just leave some comments below, and we'll try and get back to you as soon as possible.